Okay. All right, so we're going to be starting the next section here today. Hopefully the homework's going okay for you. Please keep up because the test is a week from Thursday. So it'll cover everything through 2.5. So we're going to start 2.4 today. But I thought, to start it out, what we would do is look at a specific example. Over here I've listed out the important derivatives that we talked about last class. First one is the power rule. Everyone needs to be very familiar with this rule now. Then derivative of sine, derivative of cosine, and then this last one just says, remember, if we have two functions that are being added or subtracted, if we want to take the derivative, we can take the derivative of each one individually, which is nice. But now let's take a look at this function here. And we have two functions, x and sine x, that are being multiplied together, right? So we have a product. And so it does not look like this here. We don't have addition or subtraction. So the question becomes, how do we find the derivative of this, right? Well, you might think what you can do is just take the derivative of each one of them separately. So let's just see what would happen. If we take the derivative of x, the derivative of x is 1, okay? 1 times the derivative of sine of x, which is cosine of x, and that's just 1 times cosine x, so this is cosine x, right? Okay, well, I've graphed the function here for us, all right? I've graphed it. Let's see if this answer is right. One way I could check is I could say, all right, well, what is the derivative of this function at 0? So according to my derivative, right, if I plug 0 into this, cosine of 0 we all know is 1. So this should mean that when I go look at that function and I go to the x value of 0, that the slope of the tangent line there should be 1. And if I look at this graph, if I go to 0, which is right there, this point, and I look at the slope of the tangent line, the slope of the tangent line is not 1, right? The slope of the tangent line is 0. So this is not right. Something is wrong here, right? So it's my opinion, and I think you'll agree with me after I show this to you, that calculus would be a lot easier if this were the case. If you just, when you have a product, you just take the derivative of each one separately. That would be nice, but that's not the case, all right? It does not work that way. And so we have to figure out, how do we determine the derivative of this? And that's what today is about. Understand? Okay. So here we go. The product and quotient rules. That's all this section is about. All of the rules up to this point have been pretty straightforward. I mean, I did have to prove that formula to you, right? I had to prove that, and that was that Pascal's triangle, and it was kind of cool, but we got the formula. And then I proved the derivative of sine was cosine using a sum difference formula from pre-cal. And then this one, I didn't really prove it to you, but this one behaves the way we hope it would, right? Two functions added up, take the derivative, just do them separately. So this new idea of product and quotients and how we take the derivative of those is going to result in something that we aren't going to expect to see. And the formula is here, but let's not worry about the formula. I'm going to derive the formula. And I'm going to show you something pretty crazy, all right? So here's what I want to do. We wish to find a formula for the derivative of f of x times g of x, right? We want to know how would we take the derivative of two things being multiplied, right? So we go back to the limit definition of the derivative, which is that real ugly one. Remember the limit definition, if you say what's f prime of x, We said this is limit, h goes to 0, f of x plus h minus f of x all over h, right? That right there is the formula we all have burned into our heads now, right? But that's not what I want the derivative of. I want the derivative of two things being multiplied, right? So I'm going to call this right here, I'm going to call it capital M of x. I'm going to call it that because multiplication, I'm going to use m for these are being multiplied. I could have used any letter. So do you agree that I want to know what the derivative of capital M is? You agree with that?
Yes.
Okay, so let's do it. The derivative of capital M of x should be the limit as h goes to 0 of capital M of x plus h minus capital M of x all over h, right? That's what it is. Just using that formula, we're using capital M instead of little f. Agree? Now, what is this right here? If we go back, if I tell you plug x plus h into here, that means you're going to plug x plus h here and here, right? So this becomes, I'll do it over here, limit h goes to 0. This becomes what? F of x plus h. Then what? Times g of x plus h. Agree? So that's what this is. Then minus m of x, which is those two things multiplied, just f of x times g of x. And then all of this over h, all right? So that's the definition of it, right? This is the definition of what it would mean to take the derivative of that. Now, if you let h go to 0 right now, if you do that, you're going to get 0 over 0, all right? So what do we do? What do we do? And this is the amazing part. I want you to see, I'm going to add to this 0, and then I'm going to continue to write the rest of it. And I'll talk about this after I write it down. Does everyone agree that that's the same statement?
Yes.
Yeah? I mean, you can add 0 to anything and it's still the same thing, isn't it? Okay. Now, you might be going like, why in the world would you do that, right? Like, what are you doing? All right, so just watch what I do and then we'll talk about why I do it. So now what I'm going to do is I'm going to write this is equal to the limit as h goes to 0 of f of x plus h times g of x plus h. And then here comes, I'm going to write that plus 0 again. All right, you ready for my plus 0? Plus f of x plus h times g of x minus f of x plus h times g of x. Hold on, just let me keep writing. Minus f of x times g of x. Now everything in blue is still 0, isn't it?
Yes.
Right? I mean, this is something I've added and taken it away. Now, so you're probably thinking I've lost my mind at this point, right? Like, why am I doing this, right? Okay, so historically, when Isaac Newton was trying to figure out a formula for the derivative of a product, he had to realize this step. He had to figure this out on his own. This is a very difficult step because he had to insert something in here to make it work. And the actual thought process to say, yeah, I'm going to add that in there is not something natural. It's not something that you would just be like, oh yeah, sure, do. Go ahead and just add that in there, right? That doesn't seem like something you would just come up with, okay? But that's why geniuses are geniuses, and you know, we're all, you know, just regular old people. I'm sure you're a genius in your own right, okay? But this is genius work right here, okay? So let's see why this works and what it does, all right? So the next step Let's see, I need to take a step back and take a look at this. Okay, so I'm going to write my next step. F of x plus h, g of x plus h, and then I'm going to write minus f of, I'll do it in color, minus f of x plus h, g of x, and then, where am I at here? Plus f of x plus h, g of x, minus, oh, what am I doing? I picked up the same color pen. Okay. Minus f of x times g of x, then all of this over h. So what did I do there? I didn't do much, but what did I do there? I just rearranged these, right? I just went like that. Okay, now, do you see that we have 1, 2, 3, 4 terms over a single denominator? Algebraically, we would be allowed at this point to split this up into separate fractions. In other words, like if you have like 1 plus 3 over 5, you're allowed to write that as 1/5 plus 3/5, right? That's a legal move. If you've got multiple terms up here and one term down here, you can split it up. I'm about to do that, but I'm going to split it kind of in a special way. Now I'm going to stop doing different colors. I'm just going to do all one color. So here comes my splitting of this. I have limit, h goes to 0. I'm going to do just these two terms, just these two over h. And then I'm going to say plus, and then I'm going to have just these two terms over h. So let me do that. F of x plus h, g of x plus h, minus f of x plus h times g of x all over h. So that's those two over h. And then plus, I'm going to do a different limit. Limit h goes to 0, and then these two over h. F of x plus h times g of x minus f of x times g of x all over h. Y'all good? Understand what I've done algebraically? Okay. On this expression right here, notice in the numerator we have a common factor. What is in common on the top? What do they both have, both terms? F of x plus h. Do y'all see that? We've got f of x plus h here and f of x plus h here. If that appears in both, can't I factor it out? Okay, I'm going to do that. How about the other one? What do they have in common? A g of x, don't they? Okay, so I'm going to write limit. I'm going to let h go to 0. And then I'm going to factor out my f of x plus h right here. And I'm going to put that in front of the fraction that I get when I pull it out. So I'm pulling this f of x plus h out and setting it out in front. So what's still up here? G of x plus h, what? Minus g of x all over h. Right? Okay. And then plus limit h goes to 0. Now, you said this had the g of x in common, right? So I could pull that out. And then what would be left in my fraction here? F of x plus h minus f of x all over h. Okay, are we good? So no questions on how I got to this? We're there, all right? Believe it or not, we're there. So let's see what happens now. Let's let h go to 0. Okay, if I let h go to 0, what does this become if h goes to 0? Just f of x. Do you all agree? That just becomes f of x. So this goes to f of x times, now just put that on pause for a second, plus, now let's let h go to 0 here. This is g of x, right? There is no h in here. So that just goes to g of x, right? Times, and then we have something here. Yes? What does this become if I let h go to 0? You get 0, you get g of x here, right? Minus g of x over h, right? Which you get 0 over 0. However, does that look familiar? Look at this one. Let's do this one. How about that right there? If I say, hey, take that expression and let h go to 0, right? Yeah. Isn't that the definition of the derivative? Isn't that what it's defined to be? So doesn't this right here really become, or isn't that f prime of x? Isn't that what that is? And similarly, what is this? G prime of x. And this is your formula. So look at what the formula says. If you have two things being multiplied, right? And you want to take the derivative of this, what you will do is you will not take the derivative of one of them, right? And then multiply it by the derivative of the other one. Then you will add to that switched around. The derivative of, leave the second one, g, alone, and then take derivative of the f one. Do y'all see that? It's like you take derivative of one of them, leave the other one alone, then you add to that, you switch. Does that make sense? That is the product rule. Now, I'm going to write this down again, but this is the way you derive it. This is the method. And that hidden 0 in there is a very advanced idea. It's not something that is, like I said, normal or natural. And good thing we have people who are willing to spend years of their lives trying to figure out these things for us, right? Because then we can just use them. So here's the formula, all right? Here's the formula. The way, and there's different ways to learn the formula. You know, different books do it different ways, different teachers do it different ways. I do it a certain way. I'll explain my logic after I give you the formula. So here's what it is. Let's say you have f of x times g of x, and you want to take its derivative. Okay, does that make sense? I have a product, and I'm trying to take the derivative of the product. Then you will take the derivative of the first one and multiply it times the second one. Okay, so this is my first function, this is my second function. So I'm taking the derivative of the first times the second one, then plus the derivative of the second one times the first one. And if you're seeing this for the first time, I would recommend you memorize it this way. If you look in the book, I think they do it a little bit different. And the reason they do it different is because, you know, with addition, you can switch this, right? You can like switch this. And because these are multiplications, you can flip those also. So there's all these different variations of how you can teach this formula. That's the way I teach it. This is called the product rule. So let's say it again. If you have a product, two functions, it will be the derivative of the first times the second plus the derivative of the second times the first. The derivative of the first times the second plus the derivative of the second times the first. Just repeat that 1,000 times tonight, okay? That's your formula. Now, while we're here, would you like to see the formula for a quotient, division? I'm not going to prove that one to you. It uses the same idea. You have to do a hidden 0, but it's even more complicated, and I don't want to go through it right now. So can I just give you the formula for division? I mean, this handles multiplication, but it doesn't handle division. Division works this way. Let's say you have two functions that are being divided, like this. F on top, g on the bottom, and you want to take the derivative. This will be what we call the quotient rule. Are y'all okay with me not proving it? Okay, all right. So the quotient rule looks like this. Derivative of the top times the bottom. It's exactly the same. Minus, that's different, right? Derivative of the bottom, derivative of the bottom here times the top, like that. You see it? So very similar to this, right? You have just a subtraction. So far is the only difference. There's one other thing. That whole thing divided by g of x squared. You said you didn't want me to prove it, so I'm not. Here's the formula though, all right? So if you have two things being multiplied, derivative of the first times the second plus derivative of the second times the first. If you have a quotient, I'm going to refer to these as top and bottom, right? It's derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. We good? Y'all ready to take the derivative of that function we started class with now? So back here, you need to memorize those, okay? Those need to be memorized by next Thursday. They're on your formula sheets though. But you, as a good Cal 1 student, you definitely want to have those memorized very soon. You don't want to be referring to a formula sheet for the product and quotient rules. Okay, so here we go. We had a function f of x equals x sine x, right? So when we look at that now, the way that I will do this is I will say, all right, I recognize that I have a product right there, right? My product is occurring between the x and the sine x. So I have two functions there. This is kind of like my f of x and g of x from the formula. Now I can't say f of x and g of x because I've defined this as f of x. But these are like my two functions, right? I have the first one and the second one. So according to the formula, the derivative of that should be the derivative of this one. Watch the way I write this. The derivative of the first one times the second one plus the derivative of the second one times the first one. Does that make sense the way I wrote that? That's like, you know, f prime g plus g prime f from the formula.
Sine of x is basically g of x.
Yep. Yep. It's basically like in our formula, this was like our f of x, and this was like our g of x. But like I said, I can't use f twice because f is here. I can't really say that's f also. But yes. Any questions? You sure? All right, let's do the computation. What's the derivative of x? 1, okay, times sine x plus the derivative of sine of x, which is cosine x, right? And then times x. Now be real careful here because this x and this x can't go together, right? This x is trapped inside the cosine, so this x, the most we can do is just slide it out to the front of cosine. So my final answer is sine x plus x cosine x. That is my derivative. Now let's check. What's the derivative at 0? What should it be? It should be 0. Let's see what we get. If I replace x with 0 here, sine of 0 is 0. Plus, and then check this out. 0 here kills this, doesn't it? So you wind up getting 0. And that 0, and that we said looked like it was right. Right? Now, just because it was right here doesn't mean it's right all the time, right? Just because it was correct for one point doesn't mean we have the right answer. We have to trust that this is right. One thing we could do is we could graph it. Can't we graph the derivative? Because we know there's a relationship between a function and its derivative. Sine x plus x times cosine x. I know that looks crazy, but the blue curve is the derivative, and the red curve is the original function. So let's see, can you all remember how this works? Like if I go to the red curve, the slope of the tangent line here at the top here would be what? 0, and that means the blue curve better be crossing through the x-axis there, which it is. If I come over here, my derivative is negative, right? And you can see the graph of it is going down negative below the x-axis. And right about here, looks like right around in here, we get the lowest, the steepest, this negative number is like the steepest slope we get negative. And then it comes down, does something here, right around here, flattens out again, you can see that the derivative is 0 here. Does this make sense? So there it is. What do y'all think? That's your product rule and quotient rule. We have to just do examples now until you're bleeding out of your eyes. All right, let's do something else. Shall we do a quotient rule? Let's do a quotient rule. Let's take that same function and let me just do a slight modification to that function. Instead of doing x times sine x, how about x over sine x? Yeah? What's the derivative of this? All right, so the formula is derivative of the, here I'm going to say top and bottom because it's quotient. So the formula, let's all say it together. It's the derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Okay, so you just have to, get that programmed in, all right? So I'm going to go derivative of the top times the bottom minus the derivative of the bottom times the top. I almost forgot to put my derivative on this when I said that. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom sine x, that thing squared. Which is, let's see, what does this turn out to be right here? Pardon? Yeah, and there's no limit. Remember, the limits are gone. I only am using the limits to prove the formulas. Once we have the formulas, we don't have to use the limits anymore. So what is, yes?
Would anything be undefined? I know it might be.
Yes, this function does have a domain. Like it has a restricted domain.
Yeah.
Is that what you're?
Once we use the limit to find out the formulas, was there anything?
Yes, well, I mean, you can only find the derivative of a function where it's defined, right? So if your function isn't defined somewhere, you can't talk about the derivative there. So like right now, obviously I cannot plug 0 into this, right? So the derivative at 0 doesn't exist because the function doesn't exist there. I think that's what you're saying, yes. So there are restrictions on those formulas that they're only valid when the function is defined, right? Okay. All right, so what does this become? What's the derivative of x times sine x? 1 times sine x, so that's just sine x, right? And then minus derivatives of sine is cosine times x, but then all of this over sine x squared. I'm going to write it like that. That's the same thing, isn't it? Okay, and then I guess we could leave it like that. I'm going to do one more thing. Sine x minus x cosine x. I never like to leave an x off the tail of something like this because then someone might accidentally squeeze those together. So I just stick it out front and there it is. That's our derivative. Questions? Yes. So if somebody wanted to know the slope of the tangent line for this function at, let's say, pi over 2. What's the slope of the tangent line for this function at pi over 2? What would it be? Well, we plug pi over 2 in there, right? So that's sine of pi over 2 minus pi over 2 times cosine of pi over 2 over sine of pi over 2 squared. I guess I can put that in there. So what's sine of pi over 2? 1 minus pi over 2. What's cosine of pi over 2? 0. So that's going to be pi over 2 times 0. And then all of that over, we already said sine of pi over 2 is 1. And then we square it, so 1 squared is 1. So what's our answer? 1. So if I go graph that, and I go to the point x coordinate pi over 2, and I go to the graph, I should have a tangent line that has a perfect slope of 1. Do you believe it? You want to see it? What? Let's see it. There it is. Okay, so what is pi over 2? Let me see here. Pi over 8. Okay, I think you can see that. The red is my original function. Here's pi. Here's pi over 2. If I go up, the slope of that tangent line is 1. All right? Let's add one more layer to this problem. Same problem I have right there. I'm going to ask you something different now. Starting here, find equation of tangent line at x equals pi over 2. So what have I added to the problem now? Like if I would have presented this, like this was the problem as it appears on a test, then what would be the first thing you have to do? You have to do the quotient rule, right, and get the derivative, like we just did. And then you would plug pi over 2 into it, and you would get a slope of 1, right? But that's not what we're asking for here. What are we asking for? Equation of the line, right? So that means we have to use that formula y minus y1 equals m times x minus x1, right? This formula, this gives us the equation of the line. What we did prior to this question, the answer when we got 1, all we got there was m, right? So this question we have to do one more thing. We have to actually fill in m as being 1, and we have to figure out, you know, this right here, we need the point. We need to know what point we are, where we are on the graph. Do we know any of these right now? Do we know x1 or y1? We know x1. x1 is what? Pi over 2. What we don't know is the y coordinate. Y'all agree? You understand that? So I know that this is, you know, x minus x naught. X naught was pi over 2, but the y1 was not given to you. You have to go find it. How are you going to find y1? Plug in what? Plug pi over 2 into what? We're looking for the point on the curve, right? On the curve, not on the derivative, on the curve. So we have to plug pi over 2 into this. So y1 for us is f of pi over 2, not f prime. F of pi over 2. It's what you get when you plug pi over 2 into that. What do we get? Pi over 2 over sine of pi over 2. What's sine of pi over 2? 1. So this is pi over 2, isn't it? So this is y minus pi over 2. That's the equation of the line. Does that make sense? Yes. It just so happens that these are the same. In this problem, it just so happens not always going to be the case. All right? You're given this, you have to go find this. We've done this before, right? This is not new. Just maybe it's been a while.
Probably help as a refresher if we briefly mention that f of x is equivalent to y.
Yeah, this is always y, right? This is, you know, we've always looked at f of x as being your y coordinate. All right, so now if I go back to that graph, if I ask the computer to graph that line for me, y minus pi over 2 equals 1. I'm going to type it exactly the way it is. X minus pi over 2. What should happen here when I hit 2? When I finish typing this in, what is it going to draw? A line? Right? Where though? Here's pi over 2, right? It's going to draw me the line that goes through that point in its tangent, right? It should draw that line for me. There it is. Okay? We found the equation of that line. That's different than asking for just the slope, right? When we say f prime of pi over 2, our answer was 1. That's not an equation of a line. That's just the slope of the line. The equation of the line is what we just did. So on a test, when I'm asking you, you have to know what I'm asking for. Because if I ask for just the slope of the tangent line, you don't have to go find the equation. But if I ask for the equation and you give me the slope, that's not enough. Understand? All right. As you might imagine, this can start to get pretty complicated because now we've opened up the amount of functions we can find derivatives of. So let me open up the book because I want to stay somewhat within the difficulty level of what the book is asking you to do. I still think these are pretty lame. Okay, but we'll go baby steps, I guess. How about this? Let's say y is equal to square root of x times tangent x. The instructions here, what I'm asking for here is for you to just find y prime. That means I just want the derivative, right? I'm not asking you for the slope of a tangent line at a specific point. I just want a formula for the derivative of that function. So you look at that now, and you must realize that you have a product here. That's on you. You have to look at it and recognize the product. And the product here is occurring right there, right? There's where you have your product occurring. So you have a first function and a second function. So my derivative should be the derivative of the first one times the second one plus derivative of the second one times the first one, like that. And this, well, what's the derivative of the square root of x? Well, that last class I told you I wanted you to memorize it because we are going to use it a lot. And it's 1 over 2 root x. So you go back, refer to your notes from last class. This is 1 over 2 root x. That's the derivative of this. Then times tangent x. And then plus, now what's the derivative of tangent x? That was one I said you should try and memorize. I said you have to have these memorized. Okay, those should not require you going to your formula sheet. Tangent x is one you should have memorized within the next week or so. All right? The other three, don't worry so much about. Memorize them by the time you're in Cal 2 maybe. All right? So if you don't know what derivative of tangent x is right now, you can refer to your formula sheets, right? Your reference sheets, and it has it there. But I told you last time it's what? Secant squared x. All right, so the derivative of tangent x is secant squared x, and then times root x. And even though I'm okay with that, I'm just going to rewrite it as in a different form. I'm going to put this as tan x over 2 root x plus root x times secant squared x. So all I did there was, put these two together. So I just slid the tangent on top. And then here, again, I don't like these next to each other. I like to move this out. Remember, that x is trapped, so you got to move the x out, root x out in front. So there's your derivative. So that's what we're looking for. Box it up. Questions?
Can we do anything with secant squared?
What do you mean, do anything with it? Like, into what though? What would you want to turn secant squared into?
I know there's sine squared plus cosine squared equals.
Okay, so like a Pythagorean identity?
Yeah.
You could, but I think that would become more complicated because then you'd have two terms, right? Wouldn't you now have two things instead of just one? Yeah, and so you could also do this. This is actually 1 over cosine squared. You could do that,
Okay, I see.
right? Like secant squared, just so everyone's clear on this, secant squared really means secant x squared, right? But that really means 1 over cosine x squared, because secant is 1 over cosine from pre-cal. So this is this, right? And then when you square a fraction, you can square the top and bottom. So that's actually 1 squared over cosine squared x. And when you square 1, you just get 1. So this is secant squared x, right? This is this. But I don't think that's any prettier to look at, right? So I think we're good with this. We just leave it like that. Now, down the road, we will be setting these equal to 0 and trying to solve. So we will have to mess with this eventually and do some algebra and stuff, but for now, we just want to make sure we can compute the derivative. All right. Now, last class, I proved to you the derivative of sine was cosine, right? And I said the derivative of cosine being negative sine. I didn't prove that to you, but I said the proof was exactly the same as the proof for sine. You use a sum difference formula from pre-cal. I'm going to prove to you right now that the derivative of tangent is secant squared. Okay, I'm going to prove it to you. But I'm going to prove it to you in a slightly different way. Just watch. Let's say that y is equal to tangent x. And we want to find y prime. And let's say that I never told you the derivative was secant squared. All right? And let's say that you don't have a formula sheet to look at. How can we come up with the fact that this is derivative is secant squared? Now, we could do the limit, couldn't we? Set up the limit, h goes to 0, and do all that stuff, and it would probably be pretty nasty. But do you agree that tangent x is sine x over cosine x? You agree with that? Okay. Then if we ask for the derivative, then we can actually look at this as being a quotient, can't we? It's a quotient. And so what is the derivative of a quotient? Derivative of the top times the bottom minus derivative of the bottom times the top all over bottom squared. Y'all agree with that? Now, in order for me to prove that the derivative of this is secant squared, we all have to, I guess, be okay with the fact that we know the derivative of sine and cosine. All right? If we're okay with that, we can continue. And I proved those to you, didn't I? I mean, I basically proved that one. That one I said we could prove. So I'm just going to keep going now. What's the derivative of sine x? Cosine x. So I have cosine x times cosine x again, which is cosine squared x. And then be real careful here. Well, I better write it. Minus, you know what? I better write cosine twice. Okay, that's the first part. And then minus, now what's the derivative of cosine x? Negative sine x. So watch how I write this. See, I put it in parentheses, right? And then I'm going to on the next step. Yep. And then all of this over cosine squared x. Now this becomes cosine squared x. And then these two multiply to sine squared, right? And then minus a negative is plus. So it's plus sine squared x. And I hope the little light bulb in your brain went off. The numerator is 1. This is your Pythagorean identity from pre-cal, the most important Pythagorean identity that's out there. Sine squared x plus cosine squared x is 1. So the top is 1 and the bottom is cosine squared x. And I just showed you a second ago that this is secant squared x. And that's how you prove derivative of tangent is secant squared x. Understand? Now you don't have to do that proof. I'm just showing you we could do this now. Like if you wanted to prove what the derivative of secant was right now. Okay? Right? If I want to say, hey, what's the derivative of that? You just look on your formula sheet. But if you didn't have that, what you could do is you could rewrite secant as 1 over what? Cosine, right? And then you could do the quotient rule on this. Derivative of top times the bottom. And then when you did it all, after you did all that, you would see that the derivative of secant x is secant x tangent x. That's what it would come out to be. I'm not going to go through the work, but it would work out exactly like this. All right? So I want to just show you something. I want to show you how the book presents the formulas, all right? And this is not to confuse you, but I do think that there's something important here to talk about. The book, you don't need to write this down. The book says this: if you have two things being multiplied, and you want to take the derivative, that it is this plus this. And that is not the way I presented it to you, right? That's not the way I presented it to you. Now, let me explain why. This is how they show you the quotient rule. I think on the side here I'm going to write the way that I taught you. Okay, and then on this one, okay, here's my way, here's the book's way. Why is my way better? And I'm going to say it's better because I've been doing this too long. That's way better than this. Why? Because they're almost identical. There's only a few things you have to remember, right? Change that to a minus and divide by g squared. That's the only difference between these two formulas. The way the book presents it, they look like completely different formulas, right? Like this and this look completely different. I mean, there's similarities, but it's f then g prime, then plus, then g prime, then, f times g prime plus g times f prime. But then in this formula, it's g times f prime minus f times g prime. So they've switched it. So if you're learning it, this is the way I learned it, okay? When I was a student, I felt like I had to remember two different formulas. But then I realized, well, this is the same thing, right? This is exactly the same thing. It's just addition. I took these and I did that. And then I flipped the order there, and I flipped the order there, and that's this one. And then they're the same thing. So I think this is easier. I'm telling you this because if you go to a tutor or you go get help and you've got a friend that you're working together, maybe they're taking Cal 1 with someone else and y'all are working on product rule, they are most likely going to be using these two formulas, even the tutor. So you pick, okay? But do you see the logic behind doing that instead of this? All right, you choose whatever you want to do. More examples. We need something that's going to make you hurt a little bit. Maybe we won't go too painful yet. All right. Find y prime. Okay, there is nothing that you can do from last class to this. There were some problems in your homework where you might have had like, I don't know, this. If I gave you this over like x squared, you could do this using just what we learned last class because you could just split it up into three fractions. This over this, this over this, this over this, and then to do each one of those individually. But because I have multiple terms in the denominator, you can't do it. And so you're stuck with just the product rule. I mean, product or quotient rule. So it's obvious that that's a quotient, yes? Okay, so we have a top and a bottom. So the derivative of this should be the derivative of the top times the whole bottom in parentheses. Look, the whole damn thing's going in parentheses because I have to multiply these two, right? And then minus the derivative of what? The bottom times the top in parentheses, the whole thing, all of it over the bottom squared. Whoa, what happened there? There we go. All right, so that's me just setting it up, and now it's time to take derivatives. So the derivative of this piece right here is something from last class. We have multiple terms separated by addition and subtraction, so I can do them individually, and each one of those I can handle using the power rule, right? This one, power rule. This one, power rule. This one, the derivative of a constant is always 0, right? So let's do that. So what's the derivative of that? 3x squared, and then minus 4x, and plus 0, so I'm not going to put it. Close the parentheses, but you need it in parentheses because it's two terms, right? Okay, times x to the 4th plus x minus 4. I'm not touching that. I'm not taking the derivative of it. I'm just leaving it alone. And then minus, now, derivative again. This piece. Same story. We have multiple terms. We can do them one by one. So 4x cubed plus 1, right? Derivative of x is 1. And then minus derivative of 4 is 0. So that's it right there. And then the rest of this. And then all of that, right, over all of that squared. This is what I'm going to refer to as the raw derivative. That is the derivative without any simplification, right? There it is, just the raw form of the derivative. On your exams, 70% of the problem, of the credit for the problem, is you getting to the raw derivative, right? The next 30% is you simplifying it. So we have to clean this up. So I'm going to do what you don't want to do right now, which is expand this. And then expand this. Collect all like terms. Now I'm not going to expand the bottom. I'm just going to leave it as this square. Just leave it like that. All right? That sound like fun?
Yeah.
This is the tedious part, okay? This is the real tedious part of this, is actually simplifying this. So y prime is equal to, all right, this times this, let me see, 3x to the 6th plus 3x cubed minus 12x squared. I'm halfway through the first one. Now this, so minus 4x to the 5th minus 4x squared plus 16x. Oh, now the danger zone. Now the danger zone. It's minus, right? It's minus whatever this comes out to be. So what I would do if I were you is put your minus sign, put a bracket or a set of parentheses, and figure out what all that shit is first, and then distribute your negative through. All right? This is where most students make the mistake. That negative sign screws them up. All right, so let's go ahead and distribute that. 4x to the 6th minus 8x to the 5th power. That's 7, yeah, I kind of messed it up. Plus 28x to the 3rd plus x cubed minus 2x squared plus 7. That last one was pretty easy because it was a 1 going through everything. Questions on that? Okay, let's distribute the minus through. Yeah. And this is the first time I've done this, so I'm just gonna write it all out again. Okay, come on. All right. We only have like, what, 12 terms up there or something? Yeah, no, we're not going to. We're going to leave that alone because this is actually, if you multiplied it out, then one of the things we would want to do later is try and put it together, back together as like something factored. This is actually, that times itself is technically factored. So we're going to leave it. It's just the top is not because we have to combine it all together. Maybe when we put it all together, we can factor it. I don't know. We're going to have to see. Let's see here. Let's start out with the highest power of x, which I see is x to the 6th. We have 3 of them there, and we've got minus 4 of them there, right? So we'll have minus x to the 6th. Okay, I've got those. Okay, x to the 5th. Got that one. I've got that one, right? So how many of those? 4 of them, so plus 4 x to the 5th. Okay, took care of those. X to the 4th. Don't have any. X to the 3rd. Got that one. And this one, right? Oh, and this one, yeah, good thing. That one. So how many total do we have here? We have 3, then take away 28, then take away 1. So what is that? Negative 26 x cubed. Okay, got that. Cubes are gone. How about squareds? So negative 12 minus another 4 of them, and then plus 2 of them. So what is it? Negative, those two are negative 16. And then, I think you said negative 14 first. Negative 14x squared. Almost there. X's, I just have 16, right? So plus 16x. And then minus 7. All over your denominator squared. There we go. There it is.
Can we use multiple pens in the test?
Yeah, sure. So, yeah, that's pretty ugly derivative, isn't it?
Would you then just use synthetic or long division to solve that?
Well, I guess there's a lot of things we could think about doing to this at this point, but all we want at this juncture is to just be able to take the derivative, maybe clean it up. This is now cleaned up. We just leave it alone for right now. So don't forget what this is. This is a new function, right? If you give me a value of x and plug it in here, it will tell you the slope of the tangent line on that original function. And that original function that I put up there is a pretty nasty looking function. What was that function, by the way? Can you tell me? Because I'm going to type it in here.
It's negative x to the 6th.
No, the original
It's x cubed
x cubed
minus 2x squared.
minus 2x squared